All right, so there it is. Any questions? Saw a few erasers working. Maybe an algebra mistake here or there or something. Now, you know, I always like to write it in the F notation first. It's easy. That's what I memorize is that F notation, F of A plus H minus F of A. So if that's a 3, I just always like to write that first because then I can say to myself, okay, F of 3 plus H means plug a 3 plus H in for X. And so then I can go and write it all out there. You know, you don't have to have this step, you know, there. But anyway, you got to make sure to distribute that negative through there, right? The 3 plus H when you put in that X. That's always a problem that people forget about. Because then you might end up with 13H here, right? Instead of 11H, okay? And then your answer would be 13 instead of 11. All right, so that's the slope. Now, we do know our shortcuts now, so we can check, right? We can actually check this answer. I mean, F prime of 3, all we got to do is F prime of X, right? So what's F prime? This would be 4X minus 1, right? 4X minus 1, derivative of that is 0, so 4X minus 1 is a derivative. Plug a 3 in. 12 minus 1. What? Right? So we should have known.
Know if we're right.
You can at least know that, hey, I should get 11. You know, I should get 11. So, you know, we could do the power rule. Now, let's do a very similar one to that. Another thing I could ask you on definition of derivative would be this. So let's say we had the function sine x, and I said I want you to do f prime of 2. But I said I want you to use the definition of derivative. Okay? Now, let's go ahead and set that up. So it would be limit as h approaches 0, f of 2 plus h minus f of 2, right? Just using our definition. Right? So I give you the function sine of x. And so what's f of 2 plus h? Sine of 2 plus h. Minus, what's f of 2? Sine of 2. All over h. And before anybody gets carried away here, you cannot distribute a sine. Right? That is not multiplication. Sine of 2 plus h. Okay, so in case you were thinking that, get that out of your head. Okay, you cannot distribute sine. So this is simply sine of 2 plus h minus sine of 2. There's no algebra we can do to this. There's no conjugate, there's no algebra we can do to this. Okay? I mean, there's some rearranging we could do and use some trig laws and stuff, and we might do that later at a later time. So there's nothing you can do. So I wouldn't ask you this on the no calculator part. Right? The one we just did, that would be in the no calculator part, use the definition derivative, work it out. This would be in the calculator part. This would be like what you did on your worksheet. I would have said use the definition of the derivative to set up a limit for f prime of 2, then use your calculator and a table to find the limit. So let's do that. So pull your calculators out, and how did we do that? How would we do something like this on our calculator? With a table, right, graph it. So we'd go into our graph screen, and what would we put in as our function? The blue part, right? We would put the blue thing in to graph, except instead of h's, we would put x's, right? Remember the last worksheet we did, this is what we did. So the directions would be use the definition of the derivative to set up your limit for f prime of 2. So you would set it up But now, since there's no algebra we can do to work it, we'll go ahead and go to our calculator. So we go to the calculator screen. Oops. And we would put in sine 2 plus x minus 2. And we would graph that, and we would hit Control T to give us a table. And maybe your table's already set. Mine isn't set anymore, so I'm going to have to go to my menu, my table settings. Right, so we all need to be able to do this. I want it to be 0. Now wait, where's my table start? 0 or 2? The limit is approaching 0. The 2 doesn't have any good. That was in the 2 plus h. That's where the 2 came in. The limit is h approaches, or in this case x approaches 0. So we got started at 0. And then this down here, we put 0.0001, and then arrow up a couple. And what does it seem to be approaching? Negative 0.416. And we don't care about the undefined there, right? If that was a German short hair, or if that was a 21, or whatever was there, we wouldn't care about. The limit is approaching negative 0.416. So our answer is negative 0.416. Now again, just like the previous problem, so this would be the slope of the sine graph at 2, right? But remember the previous problem, we already know what this answer should be. What's a derivative of sine? What's a derivative of sine x? Cosine x. And so f prime of 2 would be just take a 2 and plug it in right there. Cosine of 2. Go to your calculator side of things and put in cosine of 2. Right? Cosine 2, hit enter, hit control enter, negative 0.4, that's it. Right? So we did know, I mean, it makes sense that that's what we got. All right? But so there's the two different types of definition of a derivative problems you need to be able to do.
So
one where you set it up and do the algebra, that would be no calculator. One where you set it up and use your table.
We would just have to copy the table.
And then, yeah, and if I said justify using a table, then you would copy your table down, just like we did in our worksheets.
All right.
Yeah. Yes, and I would want to see the table, absolutely, because you could get negative 0.406
Yeah,
a lot of
what
ways.
I-
Yeah, you could get that the way I showed you, just cosine of 2 or whatever. Or you could just type this limit on the screen. So I would want to see the table. And there'll probably be some limit problems that don't have anything to do with the definition of the derivative. They're just limit problems. And it'll say, justify using a table. And so that's just like the worksheet. I just want you to graph the limit, just like we did, and then copy down the table. Yes,
How do we do this other side of the worksheet?
same way.
Same way?
What we
Tables
just
and
did.
everything?
The one it says limits and derivatives, so every one of those looks like this with H's in it, right? So you just do what we just did. You type in
Oh,
this,
table.
use X instead of H. Now, I didn't make people write the table on that side,
Okay.
but on the quiz you would, because there's not as many. You already did that whole page right in the table, so I assume you know how to do that. Okay? All right, so those are the definition of the derivative ones. All right. What about, what else do you want to see? You want to do one of those chart number line? You want to practice one of those? Okay? All right, so let's take this function right here, and let's do, let's do 2x cubed minus x squared minus 3. Okay? And we want to find local max min. Now, a lot of times I'll just say find local extrema, which means find local max min. And I would put both of them in there. Okay? All right, go ahead and go. Find the local max min, find where it's increasing, decreasing, that kind of thing.
Got it done.
There's a little bit of it worked out. I think I did that.
Is your problem that allows user calculator when you plug in zero
That's a good question.
No, you just
I don't really know how to
Gotta-
plug like 1/6.
Then
then don't use this.
then don't use 1/6.
Well, I don't.
Use
1/3 is
1/4.
1/3 is 0.3 repeating. So how about 0.1? 0.1 would be easy to plug.
Yeah.
Question was, you get one like this with a weird fraction. I just made this one up here on top of my head, so I might probably have it come out a little nicer if it was no calculator. Although this one isn't bad. I mean, this is doable. And it is possible on no calculator. You have to do some fraction stuff. You have to do some decimal stuff without a calculator. Remember, we said you get this calculator or you get nothing, right? If there's no calculator, you can't use anything. So is everybody okay with what I got to there, right? And so then we put those on the number line so you can see exactly what, Jake's talking about. Now, here's the thing. I might put one like this on the calculator part because let's talk about how different this problem would look in a calculator versus a no calculator. And the quick answer is it wouldn't look different at all. It wouldn't look different at all. if I ask for the local max, though, you think about this, well, gosh, if he lets me use my calculator, I could just graph the original function. I could trace, and remember, it even shows you where the max and mins are. And I could just trace and write that down. No, you can't. Because what you do is you get points, right? You get points for doing the derivative. You get a point, right? There's only 1 point for the answer, and on the AP test, the point, your answer points only are given if you have the supporting work, right? So a right answer in a problem can be worth nothing if you haven't done the supporting work. So this may show up on the no calc. Sometimes I'll put a problem like this. I'll decide whether it's on the no calculator or the calculator part just by based on which page has room. You know, oh, I got some room on the calculator part. I'm running out of room on the no calculator part, so I'll put it in the calculator part because this problem doesn't matter. Now, it's nice if you do have your calculators, yeah, you'd be able to plug in a 1/6, so that would be nice. That would help a little bit. And to be honest, the calculator will solve for you. It'll do derivatives. So, I mean, hopefully we can all do this derivative. But if this was on the calculator part, I've shown you that on the home screen. You could literally go in and have it do the derivative for you. You could actually solve this equation, right? Under the algebra menu, we could solve this. But that would all have to be written on your paper. If you were going to do it on your calculator just as a check, it would still have to be written down. Okay? Now, technically on the AP test, you could probably leave off this line. Right? It's okay to use your calculator to solve an equation on the AP test. But you have to have the equation written down that you're solving. So once you did your derivative and wrote down that, you could go to your calculator, tell it to solve, and then write down this. So that would be the only line that would probably be different if you're using calculator or no calculator. Okay? So obviously no calculator can do this, so you got 0, 1/3. So I just thought to myself, 0.3 repeating. So 0.1 would be in between, and that's pretty easy to plug in right here. Okay? So we're going to plug in. So I did -1, I did 0.1, I did 1. So we come over here to -1. So 2 times -1, that'd be negative. -3 minus 1, that's negative. So 2 negatives make it positive. Put in a 0.1. 2 times 0.1 is positive. 3 times 0.1 is 0.3 minus 1. That's negative. Positive times negative is negative. And then put in a 1. 2 times 1 is positive. 3 minus 1 is positive. And so both positive. So now it depends on the question. Once you have this, you can answer all kinds of chart questions. Where's it increasing? Well, negative infinity to 0 from 1/3 to infinity. Where's it decreasing? From 0 to 1/3. Where's the local max? At x equals 0. Right? You would have to write this. Now, we said, whenever you do that, though, you've got to have this justification on there. Whenever you do local max or local min, and I'll try to remind you the directions, say justify your answer, this is what I mean. So x equals 0 is a local max. Since f prime changes positive to negative, f changes increasing to decreasing. And then your local min would be the reverse of that. Local min is at x equals 1/3, and then it's, negative to positive, decreasing to increasing. That's what we want to have whenever we do a local max or local min argument. Okay? All right. So that's kind of a chart kind of thing, and if it was on the calculator part or the no calculator part, you still would have all of this same justification. Very important. I'm glad you asked that question because that dawned on me that, hey, you still need that.
Can we go over all the algebra skills we're doing?
Yes, good question. Let's do some limit. So let's do a limit. Now we just did a kind of a factor and cancel one. That's the easy one, but the common denominator, the conjugate stuff. So let's do one real quick here. Do a couple of them. So let's go x equals, let's go x approaches 3. Let's do 1 over x minus 1/3 all over x minus 3. Let's say you had that limit right there. Okay? Well, first thing you do is substitute, right? So if you plug in a 3, you'd have 1/3 minus 1/3, that's 0. 3 minus 3 is 0. 0 divided by 0.
Didn't work. Keep going.
Keep going. Right, yeah, shoot. Darn it. Keep going. This is a common denominator one. Okay, do something to get a common denominator one. Go ahead and try that. Common denominator and cancel is what we hope happens. Whenever we have 0 over 0, we're hoping to do some algebra where something will cancel. Now there's the bow tie thing for getting a common denominator. I also talked about multiplying by to clear out the fractions. Multiplying by the common denominator to clear out the fractions. That's another option. Okay. If you're stuck, I'll give you a little glimpse of the beginnings of one method here.
So,
I'll give you a chance to finish here.
That makes sense. I think it's right. Good job.
All right. If I can just talk about this method, this was the clearing of fractions. The common denominator there is x and 3, which would be 3x. And so if I multiply the top and bottom by 3x, what happens is when I multiply that, the x's cancel, so I just get 3. When I multiply there, the 3's cancel, and I just get x. And then the bottom would just be this times this, which I don't want to distribute through. I want to leave it like that. Because these kind of cancel. Not quite, but what can you do? Take out a negative, right? And then it'd be negative 3 plus x, which is the same as x minus 3, right? You take out a negative. And so then you would have negative 1 over 3x. You have negative 1 on top, 3x on the bottom. And now you can substitute. Once you cancel, right? It's the whole thing is common denominator and cancel. Once you cancel, you now plug in a 3 and you get negative 1/9. Negative 1/9. So if you follow down with the blue, that's what that would look like. Now, if you like the bow tie or get a common denominator, well then let's do that in red. So the bow tie would be more like you bring this 3 up here, 3 times 1, and that gives you 3. And you bring the x times 1 up here, and that gives you x all over those two multiplied together on the bottom, the 3x. Okay, and that's where the bow tie comes from. And that's the 3x. Or just common denominator. You get 3 times 3, top and bottom, that makes 3 over 3x. You multiply top and bottom here times x, and that makes x over 3x. So you still get this, and then this is on the bottom. Now you invert and multiply. So you bring the x minus 3 up here, you invert and multiply. And so look what you get. You get 3 minus x on top, and then you get the 3x times the quantity x minus 3, which is the same thing we had up here. Now you take out your negative, right? Those cancel, and you get negative 1 over 3x. 3x. Plug in your 3. Now you substitute. Plug in your 3. And you get
So
your
our full
limit.
answer would be as limit.
So the full answer is limit as x approaches 3 of that whole thing equals negative 1.
What section is that?
That was 2 point. Well, we didn't really do them in the book. But that was what we did on that first worksheet we did. That'd be 2.3. There weren't very many of those in the book, really. That's when we did that algebra worksheet, and it had one of those. I think it had one of those on it that we did. And then the other. So there's the factoring and canceling. There's the common denominator and cancel. And then the last one of those was the conjugate one. So if you want to do one of those real quick,
Yep.
if we got limit as x approaches 2, let's see, wait a minute, time out. Let me change that, that's not going to work. Gotta think about this one a minute. So let's say we had,
Oh,
there we go. There we go. So if we put, so here'd be one where if we look at this one, we try to plug a 2 in, 2 minus 2 is 0, square root of 2 minus square root of 2 is 0, 0 divided by 0. So now we got to keep going. And whenever you see the radicals, that's when you think conjugate. So we've got 4 techniques. I mean, one is substitution that you always try. And if you just get a number, you're good. What if you get 6 over 0? Does not exist. Does not exist. We will say, for limits, we will say does not exist. So you get 6 over 0 when you plug in substitution, you just stop. Does not exist. If you get a number, that's it. You're done. If you get 0 over 0, you keep going, and that's when you do one of the other 3 techniques. Factor and cancel, right, which is the easiest one. Common denominator, which is easy to see because you got fractions in there, okay? Fractions inside of fractions. And then the other one, if you have radicals, it's the conjugate, okay? So this one starts out looking like this, right? Wherever the radicals are, sometimes they're on top, sometimes they're on the bottom. See, on this one, I could have just flipped this problem. The radicals would have been on top. But you still multiply by the conjugate of whatever the radicals are. Because by doing that, it makes the radicals go away. Okay? So when we multiply on the bottom here, radical x times radical x is just x. Radical 2 times radical 2 is just 2. The outers and inners drop out. And so that makes, yeah, I mean, that makes a pretty nice problem then. Now remember, on top, we don't want to FOIL those out. Right? We want to leave that factor because we're trying to cancel. But down here, we want to FOIL it out because we're trying to get those radicals to disappear. So those are gone. So now we let x be a 2. Now we do our substitution. Square root of 2 plus square root of 2 is 2 square root of 2.
So do you have to rewrite like the whole equation, limit of
No,
approaches
no.
to-
If you got the problem, you do all your work, you got 2 radical 2 at the end, you just circle it and that's your answer. You're good. Okay?
There's an all of these.
I mean,
it's just
we've really hit the major components here. I mean, we you know, the whole number line thing, with the max min, with the shortcuts, doing some of those shortcuts, doing the long way, the derivative, definition derivative, that's a big one. We talked about doing some on the table, so there'll be some limits where you do your table on your calculator. You know, we've reviewed this algebra on those. You know, and then obviously any ramifications of this that comes into play at all, you know, derivative or slope, just slope questions or whatever, because everything we do in here, like with the shortcut, is to find f prime. What's that mean? You know, what's f prime of 2 mean? You know, the slope at 2. You know, so we just be able to answer those. Oh, I know. I was going to show one other thing. Limits. Back on last Thursday, we did, when we ran through this stuff, here's these limits. Okay, so look what we've done. We talked about substitution. If you get it does not exist, common denominator cancel, conjugate cancel, factor cancel. We talked about calculator tables. And then graphs, limits from graphs. No, that's not hard at all. That's this stuff, right? And this is where you just think about the cars meeting, right? So does the limit, what's the limit here at -3? -1 for the cars meet, right? At -1. What's the limit here at 2? 1. That's where the cars meet. We don't care about that point down there, right? What's the limit here at 1? Does not exist. The cars don't meet. What's the limit at 1 from the right with a little plus sign? Means from the right. 0, right? From the left and right will always have a limit because that car will approach somewhere, right? So from the right, the limit is 0. From the left, the limit is 2. Okay, so to be able to do those right and left limits, but with a graph like that, that's fairly simple. And then same with the table, right? From the left is the top part of the table, like 2.998, 2.999 as you get close to 3. That's from the left. What are those approaching? And from the right, the bottom part of the table, right? If they're approaching different things, then the limit doesn't exist. But if they're approaching the same, and I think I had done an example of that the other day. I think we did that one the beginning of last Friday, yeah. We said, okay, if you had, I think when I first put this table up last Friday, these negatives weren't there, right? And we said, if you had a table like this, what's the limit? 5.371. It doesn't matter what the German shorthand, there's a 21 here, whatever's in here, it doesn't matter. It's what they're approaching. We said, but what if those two were negative? Well, now the limit would not exist, right? Because on this side, they're approaching negative, this side, they're approaching positive, okay? From the left would be this number. From the right, the limit would be that number, okay? So that was just a little bit more with the graphs. And then last thing, continuity, the continuous functions and whatever. Where is this graph discontinuous? Let's start from the left. It's discontinuous at -3. Why? Which of those 3 things fails?
The limit doesn't.
Well, the
of
limit
f of
exists.
The limit of f of x doesn't equal the limit of f
The
of
third one, the limit of f of x, which is down here at -1, does not equal f of -3 because that equals a +1, right? The limit has to equal the output. So number 1 is the output must exist. Number 2 is the limit must exist. And number 3 is the limit and the output must be the same. So
How
that
would
fails
the-
that one. What about -1? Discontinuous there. Because the limit does not exist, right? It fails number 2. The limit does not exist. Well, if it doesn't exist, it fails number 3 also. But you would just
How
say
would-
just say the limit does not exist.
How would f of a not be defined?
Where? That would be. Pretend that point wasn't there.
Put your hand like
Put my. all right.
It's to-
Oh, way to go, Griff!
It's on his feet.
Awesome. Oh, it's still here,
this. Yeah, well, it's not on the
but
board.
it's not on this plane.
Come on.
It's askew. Okay. All right. So.
Alright,
Alright.
I can picture it without your
You
hand.
got it? You got it? Okay. This point doesn't exist, then that's still discontinuous because f of a is not defined. There's no output at -3. Okay? So if there's
So
no
there
output
can't be a
at
hole.
-3. Can't be just a hole
There's
in the
no
drift.
limit.
Right.
There's
That-
a limit, but no.
There's a limit, but there's no output, so it fails number 1. No output. Okay, this one, limit does not exist. And so if I say, why is it discontinuous? I want one of those 3 reasons. Limit does not exist, function is undefined, or limit does not equal the output, you know, that
So-
third one.
And then how would
The
the
first one is like at -1. The second one is at -3.
No.
No, the first
I don't think
one-
the first one's
the
on
first
this
one isn't
picture at
on.
all.
No.
First one's, because it is defined everywhere.
Oh,
So if
I
you
thought the
pretend
first
this
one
one
was
isn't,
it doesn't exist.
So
the function doesn't exist.
So
No, the limit.
Oh, second one is a limit doesn't exist.
Okay, and then the third one
The
is.
third one is a
where
limit
the
doesn't
dots
equal the
at.
output,
And then
which
the-
would be like here.
So how
did
would the
the-
limit exist everywhere?
How would the limit exist everywhere if
To
the
be-
cars always met? How would it be continuous?
Well, no. How would it be different?
Differentiable means it's continuous everywhere, which means the cars would always meet. I mean, differentiable is just nice and smooth.
Yeah.
I mean, nothing weird going on at all. The cars always meet. The outputs are always there. They're always at the same place. There's no sharp points. Differentiable means, remember, the derivative exists everywhere too. So there's no sharp points. Right.
Differentiable means the derivative.
Differentiable means a derivative exists everywhere. Continuous means you just don't have to lift your pencil, basically. So remember, a V-graph is continuous but not differentiable. It's continuous because you never lift your pencil, right? The cars would always meet. The outputs are all there in the V-graph, but the derivative doesn't exist. So that's not different. Okay? All right, so those kind of things. And I got time for, oh yeah, perfect. One more just quick thought on this continuous and differentiable. We did it yesterday. The very first thing we did yesterday. It was problem 66 and 67. I guess I did mention it. Okay, you want this function to be continuous. Find A for this to be continuous. Well, for this to be continuous, when it breaks here at 2, what has to happen? They have to be the same y values, right? You can't have a gap here at 2. So you plug a 2 in for x, right? So you plug a 2 in for x. Here you get 2a plus 1. Here you get 4. You set them equal to each other. They have to be equal so you wouldn't have a gap. And so you solved it, a is 3/2. So that's where you could do a question about continuity, differentiability. And that was number 66 and 67 yesterday. Yes?
Are there any, like, practice problems in the book?
No. Yes. All the ones you've done up until now. But this one, there's not, I went to the review section. I mean, I'll write these up. But these are not comprehensive by any means. I went to the review section at the end of the book. I tried to find any that kind of applied to what the quiz is about. And these aren't necessarily even like the ones we've been doing directly. They're good problems. They make you think about the concepts of what we've been doing. But they're not necessarily problems that
you're
would be
gonna see
real
on the
similar
test.
necessarily to the test. I don't think they would hurt you to do, but you certainly could look at those. But that's all I could find. If you're looking for some comprehensive review, it would be go back to Thursday, Friday notes. The things I've been referencing here, all these notes I've been pulling up, they're all on the website, and just go back and do those kind of things.
Matt, your shoes are
Dope.
too sick.
Did you see these?
You're too sick. I haven't. This is the first time.
Oh, dang, because you weren't here